All right, welcome. We've all seen those slick videos promising a future of urban air taxis, but today, we're going to skip the marketing and get right into the nuts and bolts. We are opening up the engineering blueprint for the heart of these machines, the P13 propulsion system. This is the tech that's going to make or break the entire industry.
So this right here, this is the dream, isn't it? Quiet, clean aircraft zipping between city rooftops. It's a fantastic vision, but let's get real for a second. The one major thing holding this back from being our everyday reality isn't a lack of cool designs or smart software. Nope, it all comes down to the fundamental physics of how we store energy.
So here's how we're going to break it all down in this explainer. First, we'll define the core problem, the big wall that urban air mobility is up against. Then we'll dive into the P13 system and see exactly how it's designed to solve that problem. After that, we'll get into the details of its key components, look at the absolutely non-negotiable safety rules that drive the whole design, and finally, we'll walk through the grueling process of taking this from a blueprint to a certified flight-ready system.
Okay, let's start with that core problem. Like I said, it's not about making the aircraft look cool or fly straight. It's about a fundamental law of physics that every engineer in this space is battling. It's called the energy density bottleneck.
Here's the deal in plain English. Even our most advanced, cutting-edge batteries have a pretty low energy density. What that means is for every kilogram of battery you have to haul into the sky, you get a relatively small amount of juice. Now, for a quick hop across town, that might be okay, but for the kind of inner-city routes that would actually make money, a pure electric aircraft would have to be so loaded down with batteries it would be hopelessly impractical. And this isn't a design flaw you can engineer around. It's a hard limit of today's chemistry. So, to beat this problem, you can't just hope for a magical new battery. You have to build a much smarter system. And that brings us to the P13 architecture. I want you to think of this not just as a new engine, but as a strategic answer, a calculated move to get around that energy density problem.
And here it is. This diagram shows you the whole concept. The P13 is what we call a series parallel hybrid. That's a fancy way of saying it has the best of both worlds. It can run in series like an electric vehicle with the battery feeding the motor, but, and this is the magic, it can also run in parallel where the fuel-burning thermal engine and the electric motor both power the propellers at the same time. This flexibility is everything. It means you can use that quiet electric power for takeoffs and landings in the city, but then tap into the incredible energy of jet fuel for long, fast cruises.
Now this strategy gives us 3 huge, game-changing wins. First, you just blow right past the range and payload limits of batteries. Suddenly, longer flights are on the table. Second, you get what we live and breathe by in aerospace, dissimilar redundancy. Simply put, you've got 2 completely different ways to power the aircraft, electric and thermal. If one has a problem, the other is totally independent and can get you on the ground safely. That is the absolute gold standard. And third, the system is smart. It's always switching between power modes to be as efficient as possible, so not a single drop of fuel or watt of electricity is wasted. All right, let's peel back another layer and zoom in on the electric side of things. This whole P13 architecture really hinges on a perfectly synchronized team, a power duo of 2 very different electric motors, the P1 and the P3.
Okay, so on the left, you see the P1 Integrated Starter Generator, or ISG. The best way to think of this guy is as the system's power plant. Then on the right, you have the P3 propulsion motor. This is your muscle. This is what actually turns the props and creates thrust. They do very different jobs, but they have to work together in absolute lockstep.
The P1 is just a brilliant piece of engineering. It's a real workhorse, doing 3 critical jobs. First, it uses that high-voltage power to fire up the thermal engine. We're talking less than 2 seconds from a standstill. Then, the moment the engine's running, it instantly flips its role and becomes a generator, converting mechanical power into clean 800-volt DC electricity to run everything. And here's the really elegant part. Its third job is active damping. It creates these tiny, super precise reverse torque pulses that literally cancel out the engine's vibrations, which keeps the whole system smooth and protected.
So what about the P3, the muscle? Well, it's all about smooth, reliable propulsion. Its most important job is something called torque fill. If the thermal engine has even the slightest lag, the P3 jumps in less than 10 milliseconds to smooth out the power so the ride is perfectly seamless. Then, when the aircraft is descending, it acts just like the regenerative brakes in a hybrid car, recapturing that energy to top off the battery. And finally, it does this little high-speed dance to perfectly match its speed to the engines, which allows the clutch to engage so smoothly you'd never even feel it.
So, we've seen how the system works, how it's powerful and efficient.
But in aerospace, none of that matters without safety. And when we talk about safety, we're not talking about guidelines. We're talking about absolute, ironclad, non-negotiable laws of engineering.
Take a look at this number, 10 to the minus 9. It might not seem like much, but in this industry, this number is everything. It is the law. It represents the maximum allowable probability of a catastrophic failure per flight hour. That means the chance of a total failure has to be less than 1 in a billion. Let that sink in for a second. 1 in a billion. Every single design decision, every component chosen, every line of software written is judged against this mind-boggling standard.
This quote says it all. It perfectly captures the philosophy. You don't just bolt on safety at the end. You don't cross your fingers and hope it passes a test. No, safety is the foundation. It is designed in from the very first sketch on a napkin, making the entire system inherently safe from its DNA outward.
And designing for safety means you have to solve some really tough problems. Take this one, for example. This graph shows something called Paschen's law. Basically, as you go higher, the air gets thinner, and when air gets thinner, it stops being a good electrical insulator. For an 800-volt system, that's a huge deal. An electrical arc between components at high altitude could be catastrophic. It could cause a power failure or even a fire. And that's why every high-voltage part has to be meticulously engineered with special insulation and spacing, designed not for how it behaves on the ground, but for the unforgiving environment at 25,000 feet.
Now, being obsessed with safety doesn't mean you get to compromise on performance. And these numbers, these KPIs, they are world-class. We're talking about getting over 5 kilowatts of power for every single kilogram of the P3 motor's weight. For the P1 generator, it's over 8 kilowatts per kilogram. And look at that inverter efficiency, over 99%. That means almost no energy is lost as waste heat. That directly translates to more range and a system that's easier to keep cool. These aren't just good numbers. This is the bleeding edge of what's possible in electric propulsion today.
So, you've got this incredible design on paper. It's safe, it's powerful, but how do you actually prove it's ready for the sky? Well, you force it to run what we call the validation gauntlet, a brutal, multi-stage testing process designed to find and fix every single potential weakness long before it ever leaves the ground.
And the process is incredibly methodical. You start virtually, with hardware-in-the-loop testing. That's where we take the real flight computers and plug them into a massive simulation that just throws an absolute nightmare of failure scenarios at them. If it survives that, it moves to the copper bird. This is where we take all the actual electrical hardware, motors, inverters, wires, the works, and connect it all together on a ground rig to see how it plays together. Finally, you have the iron bird. This is the whole shebang, the thermal engine, both motors, the gearbox, all physically connected and tested as a complete system. The philosophy is simple. Prove it on the ground so you know it's perfect in the air. And these are the non-negotiables, the final red lines. These aren't goals. They are hard pass-fail criteria. That inverter efficiency must be over 99%. An emergency power-off has to happen in less than 10 milliseconds. The high-voltage bus has to be at a safe-to-touch level in under 5 seconds. And the big one, we have to prove, beyond any doubt, that the aircraft can survive any single point of failure and still fly and land safely. No excuses, no exceptions.
And that brings us right back to where we started, back to the vision. But now, hopefully you see it not just as some futuristic dream, but as the logical outcome of an incredibly rigorous, safety-obsessed engineering journey. The P13 system is the blueprint. It's the key that solves that fundamental energy problem. It's what bridges the gap from a cool prototype to a real, working commercial air taxi network. So the only question left to ask is, how is this going to change our cities?